Okay, guys, let me just get through this part, and then I will give you your packet for the chapter. The reason I have given you your chapter packet is because this is the first thing in it, and I wanted to do this first. Okay, anyway, as I was saying, on feels like forever ago, Tuesday, I was saying that there are 3 different strengths of scatter plots: strong, moderate, and weak. And sometimes it's hard for us to tell strong, moderate, or weak. So we are going to define correlation. Correlation is going to be a number assigned to a scatter plot that's going to be able to help us decide if it's strong, moderate, or weak. And it's like a percentage. So this is an example of strong positive. I know that they look kind of spread out, but the reason that this one is strong is because there's just so many dots. So the more dots, the stronger. I don't know if that makes sense to you guys. You get the more data to back it up. Strong, negative. And then this one is that like baby spaghetti thing I was talking about. No relationship, they're just kind of scattered all over. Does that make sense to you guys? Easy? Anyone with me? Is it easy-ish? Okay. All right. Good. Okay, this is why I didn't want to pass out the packet yet, because I wanted to get your opinion. Which one of these plots looks more linear to you? Left and right, so 1 or 2. Give me fingers up. Graph number 1 or graph number 2? Looking more linear. You're all being very hesitant about your answer. Okay, to be honest, there's no right or wrong answer here.
That's why I said both.
Ah, did you? Nice. Okay. These 2 plots are exactly the same scatter plot. Because we're of our human eyes, we see things in a certain way. This one in scale, it started at 0. This one scale started at 1.4. So we are easily fooled by scales or different representations. So what I'm appealing to you is now we need an actual measurement to tell strong, moderate, or weak. So the same. Okay, now I think after that I'm safe to pass out the packet. Okay. That's not it. That's a much bigger packet. You don't want that one. You're like, are you sure? Oh, I'm sure. Yeah, I will. I'm hoping this won't take super long. You don't have to write. It's a hope I have. Okay. All right, guys. So if you guys could flip to the second page on the slide that we're on, I actually really like how this printed. So it says we will use the correlation coefficient R to measure the strength and direction of the data. Okay, so R is going to be a new thing like X bar or like M or like standard deviation S sub X, something like that. We're going to have R equals, and then we're going to have a number. If R is 1, the data makes a perfect straight line in a positive direction. Look below that on your packet. So you're on the second page. Look at the graphs below. You see the perfect positive correlation one is a 1. That means 100% straight. So you gotta kind of convert it to a percent in your mind. If r is -1, the data makes a perfect straight line in a negative direction. So that's all the way over here on the right. So r is +1, r is -1. And if r is 0, the data does not seem linked at all, or it's not linear. Okay, and this is going to come back all through the chapter. Correlation, R, only applies to lines. If you have a curve in your scatter plot, your correlation is 0 immediately. The problem is your calculator is going to calculate correlation even if it's curved. So that's where one of those little things in AP Stats, you're going to have to be like, oh, calculator didn't look at the graph, it just did the calculation. So you have to be smarter than the calculator. Oh, great. Okay, and then do you see all of these guys in the middle? All of these other little graphs? 1 second. So right here, I've got R equals 1, so that's 100% strength. And then the next one, the purple one, 80% strength, 30% strength, 0. And then do you see where the negatives come in? It's going downhill. -30% strength, -80% strength, and -100% strength. So R tells you two things. It tells you if it's going up or down, and it tells you how strong it is. Does that make sense? Okay. All right, facts about correlation. Flip over your packet. The correlation coefficient R is not easy to calculate, but it is possible. We will calculate it with the graphing calculator. Now, there are folks in class that will not be satisfied with that information. So right here in your packet, we're going to put the formula for it. I am probably never going to ask you to do it. But because there are people in here in like Calc C and stuff that are going to be like, but how do we do it? We're going to write it in our packet. So in this little spot, we're going to put the formula for R. And it's so big that I don't even have it memorized. So I have to look it up every time. Okay. Here it is. Are you ready? R equals 1 over n minus 1 times all things added together, x minus the mean over standard deviation times y minus the mean over standard deviation. Okay, before we move on, you guys I already lost you, but I didn't lose all of you. I lost some of you. Okay, I want you to think about math teacher at heart here. I want to just walk through this just for a second. Just for one moment. If I could find a decent XY table. Okay. All right, let's look at this. Do you guys remember this question from your homework? Okay. This is what your calculator will do. We're not going to do it, but this is what your calculator would do. So it would say 1 over the number of coordinates minus 1. In this case, how many coordinates were there? 8. Okay, so this would be 1 over 8 minus 1. And then your calculator would say, okay,
I'm going to calculate the mean of the x's and the standard deviation of the x's and calculate the mean of the y's and the standard deviation of the y's. Then it would take each x minus the mean of the x's divided by the standard deviation of the x's times each y minus the mean of the y's divided by the standard deviation of the y's, add all of those together. Okay, I want you to think of it like this: a z-score for that particular x value times the z-score for the particular y value, all of those added together times the number or divided by the number of coordinates minus 1. Okay, the only reason I'm telling you this is because I want you to know, but also because I want you to respect how amazing your calculator is. It's going to calculate R for you in about half a second. So anyway, next, R has no units. It is just a number. You're not going to say like R feet or R centimeters cubed or anything like that. It's just a percentage of strength. R is not affected by the change of units. It's calculated using standardized values, meaning z-scores. We talked about that. Z-scores also don't have units. You don't write like z equals 1.5 feet. No units. And then there's my joke. Did you see my joke? It said the nonlinear pattern with outliers, but for some reason I'm very happy with the data. I have another joke for you too, but that one's actually probably better. Okay, more facts about correlation. R does not change if you reverse the explanatory and response variables. Okay, what I want you to think about is x and y axis. You take it, flip it like this. It's still the same strength. It's talking about a percent strength. Look at a scatter plot like this. It's 80% strength. You flip it this way, it's still going to be 80% strength. The dots really don't change. It's just kind of like their location. R is not resistant. It is strongly affected by outliers. You're going to need that in a moment. So hold that thought. Estimate R with caution when outliers appear. So if it's, I don't know, 80% strength and there's this crazy outlier, it's going to bring the R way down, closer to 0. R is 0 when it's not linear. So if you have any kind of graph with a curve in it, you don't have to think about R, it's just 0. Next, correlation is not causation. This is actually one of the most important things in stats. There can be other confounding variables to explain the correlation. Just because you graph an x and a y doesn't mean your x caused the y. You guys know about the murders and ice cream thing? Okay, this is might be a psychology thing, but if you graph the amount of murders on the x-axis and you graph the amount of ice cream sales on the y-axis, there's almost a perfect positive correlation. But murders do not cause more ice cream sales. There is a confounding variable causing both of those things to happen, and that's the temperature outside. As the temperature increases, murder increases, and as the temperature increases, ice cream sales increase. Just because those two things make a really pretty line in a scatter plot doesn't mean that they cause each other. A lot of times there's something else. Okay, and then correlation is only used for quantitative data. You have to have numbers to plug in. You can't plug in a word into an R formula. Only quantitative. Okay, now this part is not in your packet. I hope it's not. This is supposed to be kind of a fun game. So I'm going to put a scatter plot up, and I want you guys to loudly, with your voice, estimate what you think R is. You might want to flip back to that little page where those like 7 little graphs are. Don't forget your positive and negative. Here we go. Positive what? +1. Great job. Everybody good with that?
Yeah. Oh. 0.3. 0.3. Locking it at 0.2 positive 0.
Pretty, you're being harsh on that graph. That's pretty decent. Yeah. Now you can really picture a line in there. Okay.
Negative 0.3. Negative 0.3. Negative 0.3. Negative 0.3. 0.5. 0.5.
Luckily, we're gonna be able to have a calculator for, you know.
0. 0.1. 0.3. 0.3.
Who said negative?
0.1. 0.2. 0.3. Oh. Whoa. Hash me out, bro. What's this a process on? 0. 0. 0. Higher over 0. Yeah. I'm gonna take off. No. 0.6. 0.6. 0.8. Oh, but those are outliers. Oh. Okay. 0.8. I'll say 6. No. 0.
I tried to trick you. It was 0. But you didn't, you were not fooled.
Can't show blue.
Believe it or not, that's all I have for you. That's it.